Most bridge failures follow a familiar pattern. They carry more weight than they were designed for. They suffer from decades of neglect. Or they are struck by forces far beyond what engineers anticipated. The Tacoma Narrows Bridge followed none of those patterns. It was not overloaded, it was not neglected, and it was not subjected to extreme conditions. It was considered structurally sound. And yet, just 4 months after opening, it tore itself apart. Not during a storm, not during an earthquake, but in a steady wind that many people wouldn't even describe as dangerous. What makes this failure remarkable is not how dramatic it looked in its final moments. It's how ordinary everything seemed beforehand, because the engineers didn't ignore the rules. They followed them. One assumption simply turned out to be wrong. In the late 1930s, the Tacoma Narrows represented opportunity. The narrow channel of Puget Sound separated growing communities from jobs, commerce, and economic growth. Ferries were slow, unreliable, and vulnerable to weather. A bridge promised permanence. When construction began, the goal was efficiency. Engineers wanted a structure that used less material, cost less to build, and still met every known safety requirement. The result was a sleek suspension bridge with a narrow roadway and shallow stiffening girders beneath the deck. On paper, it worked. The calculations showed the bridge could easily carry traffic. Steel stresses were within acceptable limits. From a traditional engineering perspective, the design made sense. Almost as soon as the bridge opened in July of 1940, people noticed something unusual. The roadway moved. Even on calm days, the deck rose and fell beneath passing cars. Drivers described the sensation as strange, but not frightening. The bridge wasn't shaking violently. It was moving smoothly, rhythmically. Engineers observed the motion closely. They installed dampers to reduce the oscillations and continued to monitor the behavior. Nothing suggested imminent danger. Bridges had always moved. Movement was expected. What no one fully appreciated was what that movement represented. At the time, engineering education emphasized static behavior. Forces were treated as fixed. Loads were treated as steady. As long as a structure could resist gravity and support expected traffic, it was considered safe. Wind was viewed as a nuisance, not a primary design driver. If wind caused vibration, engineers assumed the structure would absorb the energy and gradually return to rest. This assumption wasn't careless. It was based on decades of experience. What engineers lacked was a deep understanding of how motion itself could alter the forces acting on a structure. And without wind tunnel testing, that interaction remained theoretical. The most important assumption was subtle. Engineers believed the bridge would dissipate energy. They assumed that any motion introduced by wind would naturally fade over time. What they didn't realize was that the bridge's shape could cause the opposite effect. The narrow deck and solid plate girders changed how air flowed around the structure. Instead of allowing wind to pass through, the bridge forced air to move around it. And that difference mattered. In many systems, motion resists itself. Energy goes in, energy fades out. But in some systems, motion creates conditions that add more energy. At Tacoma Narrows, every movement of the bridge changed the airflow around the deck, and every change in airflow applied force back onto the structure. The system became self-reinforcing. The bridge didn't just respond to the wind, it interacted with it. Engineers later called this phenomenon aeroelastic flutter, but the mechanics are easier to understand through a simple analogy. Imagine a person on a swing. A random gust of wind barely moves it, but a well-timed push applied at exactly the right moment adds energy. At Tacoma Narrows, the wind acted like that well-timed push. Each twist of the deck set up airflow patterns that reinforced the next twist. The bridge wasn't vibrating randomly. It was being driven. Each cycle grew stronger than the last. On November 7, 1940, winds reached about 40 miles per hour. Nothing extreme for the region. But that morning, the bridge's behavior changed. The familiar up-and-down motion disappeared. In its place came violent twisting. The roadway rotated back and forth, each cycle more severe than the last. There was no mechanism to remove the energy, no way to damp the motion. steel deformed, connections fractured, and eventually the central span collapsed into Puget Sound. The failure wasn't sudden, it was the inevitable result of a system that could no longer correct itself. Remarkably, no human lives were lost, but the lesson was profound. The collapse demonstrated that strength and stability are not the same thing. After Tacoma Narrows, engineering practice changed. Wind tunnel testing became standard, bridge decks were redesigned, open truss structures allowed air to pass through instead of pushing against solid surfaces. Engineers learned to think dynamically. They learned that motion itself can be a source of force. The Tacoma Narrows Bridge didn't fail because engineers were careless. It failed because the system behaved in a way they did not expect. That lesson extends far beyond bridges. Any system that assumes forces will cancel out rather than compound faces the same risk. Not suddenly, but gradually, until control is lost. One assumption, one overlooked interaction, and a bridge that forever changed how engineers understand the power of motion.